Okay, so here is our warm-up for pre-calculus. If you want to go ahead and pause it, so right now people can give them about 2-3 minutes to work on it because it can be done with the graphing calculator, and then we'll come back and go over the problems. Okay, so we're going to go ahead and determine the intervals over which the function is increasing, decreasing, or constant. So we have the function f at x equals the square root of x squared minus 9. Now the easiest way to go about this would be to go ahead and graph this on our graphing calculator and then kind of sketch it on the graph that we have here. So when we're looking at this, we actually have kind of two square root looking shapes. One starting at this -3 and then going out this direction, and the other one starting at +3 and going out this direction. And so when we're looking at the two parts of our graph, our left part of the graph, as we move to the right, from left to right, our graph is going down. So this is a decreasing part of the graph. And when we're looking at what interval that it's decreasing, we're looking at our x values. So all the way, because this keeps on going forever this direction to -infinity, this is going to decrease from -infinity all the way until it stops at -3. And because it actually includes -3, we're going to go ahead and use that brace. And now we have nothing going on. Not increasing, not decreasing, not constant. There's nothing going on between -3 and 3. And then out on our right side of the graph, it is now increasing. So it starts at 3 and then it just keeps going up, up, and up from there. And so our increasing portion is from 3, and then it keeps going on till infinity. Okay, and so that's just our warm-up, our little review problem to get that back in your head, thinking about that, because we have the Chapter 1 test coming up next week. Now go ahead and pause this and give people time to think about this one. Probably about 2 or 3 minutes. Okay, so yesterday we had talked about doing composition of functions, and so we've got the function f at x and then the function g at x, and we're trying to find the domain of the composition f of g at x. So we're going to go ahead and algebraically we're going to plug g of x into f of x. So I have my f of x, and instead of x squared, I'm going to go ahead and put that g of x in that x spot. So there's that g of x into that x squared spot. And we're going to go ahead and simplify this. Luckily, we've got the cancellation of our square root and our square. And so this becomes 9 minus x squared. And then we have the -9. And then those 9s will cancel out. And we get a -x squared. And that is the value of our composition. Helps if I write my notation correctly. Okay, so now the question is what's going on with that domain? So luckily we got that square root canceling out with the squared, and with the -x squared, it would seem like we wouldn't have any restrictions in our domain, but we still have to take into consideration this up here, because there were certain numbers we couldn't have plugged in there, and that's going to restrict my domain. And so down here, that restriction is still sticking. So that 9 minus x squared, it has to be 0 or bigger, because we can't square root negative numbers, we get those imaginaries. So when I'm looking at this restriction, I'm looking at this. And so what I can do is I can go ahead and solve this to help get that restriction on my domain. So I can -9 on both sides. I can divide by -1. And then I can square root both sides. which gives me x is less than or equal to 3. But I also have the negative option. I also have the x's. I flip that sign with the negative. And so now all of a sudden I have this restriction where x can be less than 3, but x has to be greater than negative 3. And so it's less than 3, yet greater than or equal to negative 3. And here's that restriction. And in fact, we can graph this on our graphing calculator to kind of see how that works. So let's go ahead and take a look at my graphing calculator here. Let me move it underneath the screen and see if we can get that to pop up. And it's not showing up very well. And so there's my graphing calculator, showing you how all of a sudden we are really only getting this right here. Oh, it's kind of cool. So where it's going from that negative 3 to that positive 3, that negative x squared. And if you wanted to see how I got that in my y equals, I went ahead and I put it in that original format with that g of x inside that x squared. So it went ahead and took into consideration that restricted domain. So now that graph shows us we didn't simplify, we put it in exactly in that original composition form, and it went ahead and graphed it with those restrictions. Okay, so let's go ahead and look at our next problem. If f at x equals 2x plus 3 and g at x equals 1/2 x plus 3, find the composition f of g of x. So remember that g is going to be plugged in to the x. So f of g of x. So I'm going to take the 2, and in that x spot I'm going to put the g of x. 1/2 x plus 3. And then I have the plus 3 at the end. The nice thing is that 2 times 1/2 here is going to cancel out. And this is going to become the number 1. And so now I have this x plus 3 plus 3, which gives me x plus 6. So in our second one, we're working backwards. We're going to plug the f function into the g function. So now I'm going to have (1/2), and in that x spot we're going to put 2x plus 3, and then plus 3. So we're going to go ahead and simplify this inside part, which is going to give me 1/2 2x plus 6, because I can combine those two. And then I'm going to distribute the half. Half of 2x is x. Half of 6 is 3. And we get that x plus 3. Okay, so now what we're going to do is we're going to do a little bit of creative thinking. And in these ones, you're going to find that you have multiple options here. But we're going to look for kind of simpler options. We're going to rewrite h of x in terms of f of x and g at x. So that way our composition of the two gives us h. So I'm going to go ahead and say that f of at x is 1 over x squared. And then that way my g is what's being put in that x spot right here. So my g of x would be x plus 2. And that's it. That's one possibility of what we could have done. We could have also done f at x is 1 over x, and g at x is x plus 2 squared. There's another option. So we're looking at what combinations would result in that h of x. So take a minute, pause the video, and think about example B. What could you do? Okay, so one option may be that f of x is x squared, and g at x is 3x minus 5. So this is getting plugged into that x position. You could have also done something like f at x is x minus 5 squared, and g at x is 3x. So lots of different combinations, and it allows you to think creatively. What could possibly be paired together to give us that combination? Okay, so now we're getting into where we're actually starting to combine information, and we're looking at things in context. So we have a problem where the number of bacteria in refrigerated food can be represented by n at t equals 20t squared minus 80t plus 500, where t has to be between 2 and 14. T is going to be our temperature in degrees Celsius. Now when food is removed from the refrigerator, the temperature is T at T, big T at little t, equals 4T plus 2, where T is between 0 and 3, and T is in hours. And so what we're going to do now is we're going to find the composite N at T of T. And they want to know, what does this function represent? So first thing we're going to do is we're going to do the composition. We're going to plug this in to wherever there's a T. And so we'll have 24t plus 2 squared minus 80, 4t plus 2 plus 500. Now we could go ahead and break this down and simplify it. We've been working on that enough though, and so I really want to spend time talking about what does this represent. So in this function here, we're trying to figure out what the temperature of the food is after it comes out of the refrigerator. And so T is the number of hours that we spend out of the refrigerator. And now I'm going to plug that into here to calculate the bacteria in food. So what I'm trying to do is calculate bacteria in food after it has come out of the fridge. Okay, so what we're going to do now is calculate the number of bacteria after 2 hours. So I'm going to go ahead and plug in the 2 here. So 4 times 2 is 8, plus 2 is 10, minus 80. 4 times 2 is 8, plus 2 is 10. So this is going to give me 20 times 100 minus 800 plus 500, which gives us 1,700 bacteria. Now our next question is, when is the time that the bacteria count reaches 2,000? So now all of a sudden we're getting an answer to this elaborate equation. And so we have some options to us. We've done this type of stuff before. We can go ahead and simplify it. We're going to end up with a quadratic. We could try factoring it. We could graph it. We have lots of different options to us. We could graph the line y equals 2,000. And then we can graph our line 20 times 4x plus 2 squared minus 80 times 4x plus 2 plus 500, and look at where these two lines intersect. So if we go to our graphing calculator here, we've got our 2000, we've got our equation, and then we can go into our we can go into our graph. We're going to look somewhere around 1900 to 2100, going by hundreds. So there's our y equals 2000 line. And then we see our parabola there. And then we can try and trace to estimate, or we can go in and we can calculate. And I could calculate the intersection. So I want to intersect this graph with the second curve. And right there we get that intersection at 2.220486. And yes, you heard me take a picture of that. And so then using that graph, we can see where that intersection is, and we could figure out the amount of time, 2.22 hours. And we are good to go. Okay, so going back and reviewing the difference quotient. So again, seeing a lot of these different problems over and over and over, just to remind you, especially with the test coming up. So the first thing we're going to do is we're going to plug in x plus h into our function. And then I'm going to go ahead and subtract the original function, which means because I'm subtracting, I'm changing the sign of everything in the original function. And then I divide by h. I need to go ahead and multiply out this pink part right here. So this is really 1 minus x squared, and then 2xh plus h squared. And then I have that minus 1 plus x squared, and that's all over h. Next thing I'm doing is I'm going to go ahead and distribute this negative inside. So now this is 1 minus x squared minus 2xh minus h squared. And then I have that minus 1 plus x squared. And we all know what's going to happen, but we mathematically still have to work it out. We know those ones are going to cancel. We know those x squareds are going to cancel. And that's the whole purpose of our difference quotient. And we are now left with that negative 2xh minus h squared. And since the whole thing's over h, we're going to go ahead and break that up over h so we can simplify. That means these h's are going to cancel. This h is going to cancel out with that one. So now I have negative 2x minus h. And so the idea is that the more I show it to you, the more I get you to work through this, the easier it gets each time. You start seeing that over and over and over. Okay, find two functions f and g such that the function of g of x will give us h of x. So we did these just not too long ago, so we're going to do it again. So let's see, we can have an f at x could be x squared. Since I have this squared. There's my f. And then the g of x that's going to get plugged in there could be this portion right here, 2x plus 1. And then our next one, we can say our f at x is the 4 over x squared. And then what we're plugging into it is this part right here. So our g at x is 5x plus 2. Again, a lot of different options for us, but looking at how those can be pulled apart to give us two functions in composition form. Okay, tonight's assignment, 1.4b, just practicing more of those compositions. Some of the story problems, some of them you're looking at, is it a composition when I put it together? Am I adding them when I put it together? So just think about that context. And then that is it. So we will see you next time.